Okay. If you're joining virtually, I have the links to this set of worksheets, review worksheets under chat. So if you can find it there. Okay. First view is just expanding. So we'll start with number 4. Okay, so quite a bit to expand, but we can think of this as A, B, and C. We can pull the 4 down in front first. Once the 4 comes down, then we can think of this as A, B, and C. We can expand using quotient and product property. Anything in the denominator will be part of a negative natural log. Continue bringing the exponents down. 4 times 1/2 is just 2. And now it should feel easier because everything is expanded, just a bunch of u prime over u to get to your derivative. Morning. That's the new booster.
Yesterday and I missed Friday, so I was able to do that homework.
Okay. This is working together.
Okay.
Yeah. And then right, it should be this.
Worksheet 1 and 2, you will.
They're all here.
Oh, okay.
And then this is what we're working through right now.
Thank you.
Okay. Nicole, you good with 4? Let's look at number 5 is the same thing. It's a very similar process. Let's look at something else here. Number 8. says use implicit differentiation. So even if it was not specifying that there's implicit, we still understand there's implicit because we have all these y's in the way. So expand first, and then we can move to our derivative step. Okay, from here we can find our derivative. U prime over u for the natural logs. We have 3 different y variables, so we're expecting 3 dy dx's to show up. All right, I have a separate worksheet you can pick up. This is the most important step here, getting to the derivative. After this is just adding, subtracting, rearranging, factoring dy dx. So any questions for the previous step to this step? Good. Okay, from here, we can start to collect our dy dx terms, move all the dy dx terms on the same side, all the non-dy dx terms on the other side, factor dy dx out, and then divide it over. You can leave your answer a mess. It's okay. As long as your dy dx is by itself, that's all we care about. That's right. So the first few steps, all this is just expanding. And then our derivative is just to get from this step to this step. Then from here, I'm just collecting all my dy dx terms on the same side, all the non-dy dx terms on the other side, factor dy dx out, divide over. A seemingly minor adjustments is letting that y's derivative be 1 dy dx. Right? Having that 1 is helpful because if a student doesn't see a y there or a 1 there, you may be tempted to just say, oh, 1 over 2y and dy dx get factored out, so nothing there, plus 6y. And having that 1 there reminds you that even dy dx, when factored out, there's still a 1 left over. So Yeah, so if you see y by itself, just put a 1 dy dx. That will keep you, it'll go a long ways in making sure that you don't lose track of that term. Next one we're going to try is try number 10. Number 10 is derivative of inverse at a point. We go through our chart here to kind of map our progress. Trying to find the derivative of f inverse at 17. We know that whatever number they tell you is always going to be the y value of the function you're working on. So that's where we start. Our first goal is to figure out what is the order pair, what's the x value at this level. And then once we get the x value, we can work on the derivative. From the derivative, we can find the slope. And once you get the slope, then we're almost there. Then we just have to make a slight adjustment to get from this slope value to this slope value. Okay, we go through a series of guess and checks. Try 0, 0 doesn't work. Try 1, 1 doesn't work. -1 doesn't work. Let's see, 2, 24, -4, -20. Okay, that works. Yeah, it's not always 2. It just so it just happens that the examples that we've done so far have always been x equals 2, but hopefully we understand the process, right? We just keep trying easy numbers around 0 until we get to one that works. So we've established our order pair relationship between our function and its inverse. There's order pairs 2, 17, and the corresponding point that is going to have a numeric relationship is with that order pair 17, 2. So then if I can find f prime of 2, then I can get to the derivative of f inverse at 17. So I'm going to find the slope of the f graph at 2, but first I would need to find f prime of x. Let's find our slope formula, and then we can plug 2 in. So the slope of 2 is 34, which means that the slope of f inverse at 17 will be 1 over 34. Okay, moving on to the second worksheet. Line number 3. Y equals 2e to the 5 root x cubed. We know this is just e to the u, right? So the rule for e to the u is just e to the u times u prime. We know our work is really just trying to figure out that u prime. So maybe we can rewrite that exponent to get it ready for that u prime. So I'm going to rewrite it first. And now I can jump into my derivative rule. So just remember that the rule for e to the u is you're going to copy the exact problem into your derivative. So you're always going to include the original function in your answer. And then the only thing extra, I have to worry about that u prime that's going to come after that. So this will show up in our derivative, and then go through power rule to get to u prime. Number 4. Number 4, we see some expansion that we can do with that natural log, but we also understand that there are two separate functions here. We got to go through product rule. But I can clean up that f portion before I jump into my derivative rules. Bring that radical up as a rational exponent, bring that exponent down in front because we're under a natural log expression. And now we have an easier time with that f portion, just u prime over u. Any questions here? Okay. Let's go to 9 and 10 on the last page. So now these are extensions of the parent rules that we just learned. So we're using natural log of u, this is base e. Now we have log base a of u, which we can apply with number 10. And for number 9, exponential function e to the u is related to exponential function a to the u. And if it's not base e, then we can use base a, assuming that it is a constant regular variable. So number 9 fits a to the u rule. Number 10 fits my log base a. Exponentials, you can never expand. You have to just take whatever they give you. But anytime you're inside a log function, we always want to explore, okay, can I expand? Can I make my life easier so that my derivative process can be simpler?
This one, so that is like not a perfect square.
It's okay. It still works.
Because I'm just doing it.
Mhm. You really don't have to do any cleanup from that first step. I mean, yeah. I just wanted to move all the terms in front of my exponential function, but if you didn't do that, it's fine. Okay, number 10, we see a messy log expression, just treat it like natural log. And then at the very end, your derivative rule will be slightly different, but almost the same. this is what, as far as I can go, expansion wise, then I can apply my rule after this. Again, if you didn't clean up your f prime, it's fine.
Just wondering. We flip this. Like, why do we flip? So we can count 6, 3.
Or asking for help.
Yeah, I'm wondering like, because we have 6, 3, right?
Mm-hmm.
Then we again from -5 to 5.
Mm-hmm.
And it's 5, and since that's even, it'll just be a 2.
Yeah.
It's 5, 5. Oh wait. Okay, wait, never mind. I think I put it on. Okay.
Any questions? Yeah, one more for us. This is not on the worksheet, so you guys can just put this on the separate sheet. Got it. The reason why this is log differentiation is because this is a variable raised to a variable. We don't want to get this confused with a to the u. It looks like a to the u, but the base is not a constant, right? If it was base 3 or base 5 or base 6, then we'll use that a to the u rule. But if I have a variable raised to a variable, I know there's no rule that can handle that. I got to take natural log of both sides and bring that exponent down. All right, try those steps. See if those make sense, and I'll walk through that with you.
Wanted me to just write down this last, on a sheet of paper, so I think that's what you asked me to do.
Um,
So I'll almost like to show them the recovery. So you asked me to just redo the last one. So that's why we have a 70 in the critical window, I guess. Let's do the same service last.
yeah, I would want you to come in and redo this one.
I did.
You did.
I did. I redid the whole test, I'm pretty sure. And then when I redid, I got the last one wrong.
Oh,
So you asked me to, yeah, then you just asked me to copy. Like, I
which part did you mess up?
just this question. Just gonna keep it again. You just have to make X.
Yeah. Well, now you know this. If I gave you another one, would you be able to do it from scratch?
Yeah.
Okay. You
You
know,
want, I can do one.
yeah. There's probably not enough time. You want to come
I
in
can do
tomorrow?
one tomorrow.
Okay, sounds good. Yeah, come in.
Okay.
Yeah. Yeah. Okay. Yeah. Come in back. Yeah. Make sure you can do that. I'll give you another one, and I'll bump your grade.
I can also redo the related rates one, because I have finished that one anyways.
Yeah. Just bring your original quiz so I know which ones you're gonna.
Yeah, it's this one.
Okay. Yeah, just bring that in tomorrow so I can look at it. Mhm. Okay, so after you take natural off of both sides, we also want to get that radical in a rational form. So that's 5/2. Bring that exponent down. And then we're always going to be staring at product rule on the right side because now your variable is in front of the other variable. So a little bit of implicit on the left and then product rule on the right. And then product rule, and then within product rule, there's a little bit of chain that has to be applied for f prime. Once we find the derivative using product and chain on the right side, bring the y over to the right side, and then replace the y back in terms of the original function, and then there's your derivative.
Almost one.